Okay. So this is the homework video for homework 4, module 6, electromagnetism. We're talking about application 1, simple motors and back EMF. Oops. Okay. For the first question, we've got the question is asking which component of a DC motor is responsible for maintaining the direction of torque. Okay, so it's the split ring commutator that changes current direction every half revolution to unified torque. Question 2, a simple DC motor consists of a rectangular loop of wire ABCD with dimensions 0.15 meters times 0.18 meters as shown. The magnetic field strength is this, and with this current flowing through the wire, you can simply use motor effect F equals to BIL to calculate the force. Question 3, a simple DC motor is constructed using an armature that consists of 25 turns of wire with dimensions 0.15 meters to 0.15 meters. Magnitude of the magnetic field is this much, and the current flowing is 3 amperes. The plane of the armature makes about 30 degrees angle with the magnetic field in the position shown. What is the magnitude of the torque? All right, so torque is equals to NBIA. You could apply this equation to get what you want. Question 4. The diagram shows a DC motor with a constant current flowing through the coil, which is placed between a pair of radial magnets. Which pair of graphs shows the changes in the force acting on wire P and Q, and the torque on the armature as a function of time. Okay, so the answer here would be C, in the sense that force doesn't change in magnitude, only change in direction. And so we also are given a radial magnet. It's not drawn as a radial magnet. So as a radial magnet, it should produce a more consistent torque. Okay, so C would be the more appropriate choice. Otherwise, we would go for B because we are given that we have a radial magnetic field. Okay, so ideally it would be constant torque. Okay. Question 5, which graph shows the current flowing through an electric motor as speed varies? The correct answer is D. As speed increases, current will decrease because back EMF takes away your supply EMF, so that the total current would actually reduce linearly with the speed. Okay. Common mistakes that people choose A. It's not an exponential relationship; it's a linear relationship with speed. Okay. Question 6, which of the following is correct about the function of a split ring commutator? A is the right choice, as in it maintains direction torque acting on the coil. Question 7, a DC motor is plugged into a small 12-volt battery and it's free to turn. At some point in time, the motor shaft is prevented from turning. Which of the following describes the effect of the back EMF? Okay, so if you prevent the shaft from turning, then you are preventing a changing flux, so the back EMF will actually stop existing, so it will decrease. And then there's more total EMF in the circuit, so that would lead to a current increase. D is the right answer for this. Question 8, we have a simple DC motor is constructed using a pair of parallel magnets and a single loop of wire shown. Which statement is correct when the motor is retaining a constant speed? You have a magnitude back EMF. The wire changes as the loop rotates because we don't have a radial magnetic field, so that as it rotates, the changing flux alternates like a sinusoidal wave. So if you differentiate it, the EMF should also be sinusoidal, so always be changing. Question 9, a DC motor is rotating at a constant angular velocity without any load attached. How can the angular speed of the motor be increased? You can increase the voltage, right? So this has to do with the maximum rotational speed within a motor. It's proportional to the supply EMF. Question 10, we have a coil and we pretty much have a motor, and that is used to balance a mass with a pulley. Okay, so the torque produced by the mass, which is mg times by the radius of the pulley, must be equal to the torque supplied by the coils, so that torque is balanced, and then you can suspend the mass. Okay, so you can just balance the torque. NBIA is going to be equals to mg times the radius of the pulley, and then solve for number of turns n. Should be able to get your answer. In continuation, question 11, we have a device constructed, as in like a simple DC motor, and you need to just describe each component of the structure. Okay, you have to talk about the stator, the rotor, and then the split ring commutator. Okay, so what I said that the diagram depicts a simple DC motor. It utilizes what define what a motor is, what motor effect is, right, and then how this sort of rotates in like a general principle. And I went on to talk about each segment separately. Okay. So make sure to talk about the magnet as a source of magnetic field, the rotor as like a medium that carries motor effects. There we have the split ring commutator as well to unify directional torque by changing current direction every half revolution. You could also mention about brushes that is used to connect electricity. Question 12, we have a motor, a simple DC motor. Galvanometer is applied. So when the motor is turning at a full speed, the galvanometer reads a current of 0.1 amperes. You have to explain why is that. Okay, so it's a very small current. This is because when the motor is operating, it's back EMF, right? So there's no, you have reduced the total EMF so that the current is less. So you have to sort of mention Faraday's law, Lenz's law, just to show this effect. So operating motor experiences continuous changing flux. Just outline the source of changing flux. And then by Faraday's law, yada, 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 Lenz's law, it ensures that the supply EMF is being reduced so that it's kind of like opposing initial change. Therefore, the induced EMF must be directed backward. So therefore, we have a back EMF. And then you write down this equation where the supply EMF takes out back EMF is equal to net EMF. Ohm's law tells you that equals to current times resistance. At full speed, back EMF approaches the supply EMF, and then the current will approach zero. Okay, you'll get a very small current. And also, yeah, when you hold the shaft, right, when the sudden pause is in the rotation is applied, temporal changing flux stops, so you don't have any back EMF formed. As a result, the supply EMF draws a larger current, so you would read a greater current in the ammeter or the galvanometer. Okay. Yeah. So please make sure to define the laws. Okay. Otherwise, this question is pretty straightforward. Question 13. We have a simple motor, and then question A is just to calculate the force using motor effect. Right. So F equals to BIL. Recall that force on the side of a coil does not change no matter what angle does it rotate it to. It doesn't matter. Okay, it's always BIL. And use your right hand rule to determine direction. And then question B, calculate the torque as well. Simply apply the equation. It's pretty easy. Okay. One thing to be aware is that this angle given here is the angle between the field and the plane of the coil. So, but the angle here, this theta represents the angle between the area vector of the coil and the field, which is 60 degrees in this scenario. Okay. Question 14. We have a simple DC motor that is constructed using a 50-turn loop of wire, yada, yada, yada. So describe how the magnitude of flux changes, right, as it rotates. We should include both qualitative and quantitative analysis. This question is quite involved. So the way I did this question is, again, I derived so that I used an equation to model what flux is, and I plot the function. So defining magnetic flux first. Magnetic flux is defined as a product between the magnetic field and the area vector. Phi is equals to BA times cosine of the angle. Angle is between B and A as vectors. And then in terms of qualitative description, initially there are no magnetic field lines passing through the area, so the plane is parallel to the magnetic field. So there are flux, right? As the coil rotates, the flux increases. The small components of the area is allowing magnetic field to pass through. You want to sort of explain this in a qualitative way. Yeah, this is what you do. And therefore, phi B, the magnetic flux will slowly reach a maximum, and as the coil keeps rotating, right, it will go back to a minimum. In terms of a quantitative approach, we can model the angular displacement of the coil with some dummy variable alpha, and alpha is like an angle that goes from 0 to pi, so that magnetic flux as alpha increases is modeled by BA times cosine of alpha minus pi over 2, because we have initially as a 90 degrees phase shift, right? So flux initially is 0. Right, so then that is equals to BA times sine of alpha by the trigger identity. So then you can apply your graph of this sine function for a half revolution, right? So it's 180 degrees, half revolution. And you see how phi goes from 0 and increase to maximum. You can even calculate the value for the maximum flux to be 6 times 10 to the power of -4 Webers, and goes back to 0 in like a sinusoidal function. Okay, question 15. The graph shows data for a motor connected to a 240 volt power supply. This is just a plot for some angular velocity component here corresponding to a torque. This question might be a little confusing if you if you think too much about it. It's pretty much just a graph that shows you some relationship. And then the motor is used to pull a 0.306 kilogram mass, and then the pulley's radius is 1 meter. And then it tells you an equation for the efficiency for that motor, right? It is the mechanical power divided by the electrical input power. So tau times omega is the mechanical power, right? And then V times I is the input power. Okay, and question A says that show the efficiency 0.16. So what you need to do here is you need to use the torque, right? So the torque that's required would be 0.306 kilogram of mass times by gravity multiplied by 1 meter of radius. That's the torque required to balance the mass. Okay, and then use that torque value to sort of interpolate an angular velocity value on the graph. Once you have that, then you have torque and omega. And I think voltage is given, 240 volts. Current is also given, and you can evaluate for the efficiency. Okay, so the motor is lifting the mass at a constant rate. So the torque is balanced. So again, this thing, and then you calculate torque to be roughly 3 Newton meters, and then you look at the diagram, 3 Newton meters of torque corresponding to 50 radian per second of angular velocity. Plug everything in, and you get 0.16. Okay. Question B is explain how the operation of the motor is remain consistent with all transmission energy. So you want to say energy transformation from which to which that is consistent with the observation. Okay. So the energy of the system is conserved considering that the energy diagram, right? So we have electrical power goes in, we have some power that goes to the surrounding that's lost, right? Because we have this efficiency factor, meaning that energy is an ideal, and then part of it goes to the mechanical power. Okay, so it's just sort of write an equation where the power is the whole system has a total changing energy of 0 because it's like conserved, right? So it's from your electrical power takes out the mechanical power and takes out the power losses. Okay, and sort of evaluate what the mechanical power would be. So we're sort of lifting the mass here. The mechanical power would be simply the potential energy gained by the mass as it goes up, right? So it's mg times h, that's the potential energy, and then the rate of change of it, mg stays the same, the height that changes, right? So the power mechanical energy delivered is equal to mg times dHdt, or just the velocity that the mass is traveling upward, right? mg times v. Question 16 is to plot the graph. Once again, you're given a lot of numbers, so you're required to calculate the force at least the maximum value, and then force doesn't change, it only flips direction. And torque, right, goes like this. It's an absolute value cosine function. Make sure to calculate the maximum value as well. Make sure to label as well. Make sure to label the x-axis as well, okay? It's given you 25 revolutions per minute. You can evaluate that to calculate period, which is 22.4 a second per revolution. That's a period, right? So you should label these values. And if a radial magnetic field is applied, then the torque is more smoothed out. So sort of do that. Question 17. A simple DC motor is used in a blender, and the blender is connected to a main power supply of 230 volts and draws 5 amperes of current when running at normal speed, which is the operational speed. Calculate the torque, simply substitution of the equation, and the torque is equals to NBIA. Question B says to explain the production of back EMF. That's just application of Faraday's law and Lenz's law. So it's pretty standard stuff. Question C is to calculate the back EMF that's produced. So we could use the fact that when it's at operational speed, the total voltage is equal to 0, as in back EMF is equals to like the supply EMF takes out a little bit of back EMF, and then some internal resistance is equal to 0. Okay, because ideally the coil has resistance. All right. So realistically speaking, a coil has resistance, but ideally the coil does not have resistance. So if you reach terminal speed, then the back EMF is equal to supply EMF. However, in real case, the coil has resistance. So we need a little bit of current that's left to just overcome the resistance. Okay, so we have an extra term here to make everything to 0. And then you can rearrange to evaluate your back EMF this way. Question 17 continued. D says to calculate the current drawn by the motor at startup. So that's just Ohm's law, right? Startup, we have back EMF equal to 0, so that's Ohm's law. Question E, the current cannot exceed 10 amperes within the motor's coil. Calculate the starter resistance required to ensure a safer startup. So we need to make sure that the current initially is equal to 10 amperes, right? Again, Ohm's law, make sure to include your internal resistance and then your variable resistor, okay? This is what we implement just to make sure that initially, when there's no back EMF, we still have enough resistance to ensure that the current isn't so high, okay? So the supply EMF is going to be equal to the current times by the total resistance, which is the internal resistance plus the variable resistor. Rearrange for the variable resistor is the resistance that's required for a safe current. For the challenging question, you have to talk about magnetic moments, right? So this is the foundation of electromagnetism. Magnetism generated torque is just the magnetic moment cross multiplied by the magnetic field. And we could use this to calculate the magnetic moment of a coil, right? When it's placed in a field. Question B. So we can use this magnetic moment to calculate the area of the coil, right? Simply use the definition equation given in the extension material. Okay. It's quite short for the homework this week, and it's also relatively pretty easy because the content is not very heavy. Okay. So this is it for this booklet. I will see you in the next booklet. Enjoy physics.